In Chapter 3, we will be dealing with the topic of probability, which is a big topic in statistics. Um, as we talk about probability, we're going to begin in the first section dealing with just basic concepts, learning some essential principles, and also some terminology. So as we progress through the next couple chapters, talking about some probabilities, we'll have some a vernacular, some vocabulary as our basis of discussion. In the first section, like I said, we're just going to do some basic ideas and we're going to learn how to count. Hopefully, we all know how to count, but this is going to be something a little bit different. This is counting ways that different things could occur. So, let's just start with some terminology. A probability experiment is any action or trial through which specific results are attained. So it could be flipping a coin over and over and over, or it could be spinning a spinner to see what color or what number you get, or rolling a die, or it could be drawing a marble out of a bag, or drawing an M&M out of a bag and seeing what you get. So it's something that you do and then you count the results or the possible results. An outcome is just a single result from a single trial when you do an experiment. So if I flip a coin, one outcome could be that I get a heads. The sample space is the set of all possible outcomes that you could have. So if you list all of the different things that could occur in an experiment, that's your sample space. So if you flip a coin one time, your sample space is that you could get heads or you could get tails. If you flip a coin twice, you could get heads, another heads, you could get heads and a tail, you could get tail, then heads, or you could get a tail, then a tails. So that's your sample space. Those are the different things that could happen if you flip two coins. An event is one or more outcomes that could happen. It's a subset of the sample space. So for this example, one event could be that you get both heads. We might call it event A. It is getting two heads. Or an event might be getting exactly one heads. Or an event might be getting two tails. So an event is just a specified outcome from your probability experiment. A simple event is an event that consists of one single outcome, one particular thing. So, and here's an example of flipping a coin and rolling a die. So if you flip a coin, you could get a heads, and then with a heads, there are 6 different numbers on the die that you could get. So you could get a heads and a 1, a heads and a 2, a heads and a 3, all the way through a 6. Or you get tails in each of those. So the event of tossing a heads and rolling a 3, there's one particular outcome, so that's a simple event. But if there's more than one particular outcome, then that's not a simple event. If there's more than one outcome, for example, tossing a heads and rolling an even number. If we get heads and an even number, it could be that we got heads and a 2, heads and a 4, or heads and a 6. So there are 3 different items in that subset. So there are 3 different outcomes for that event, so that's not a simple event. Now, before we talk about the counting principle, let's look at a tree diagram. And tree diagrams are used to lay out your sample space. If I have, let's suppose that I'm just randomly picking a vehicle, and that vehicle could be a Ford or a Nissan. It could be a truck, it could be a car, or it could be a van, and it could burn gas or it could burn diesel. So if I want to list my sample space of different things that could occur, then I could just randomly say I could have a Ford that's a truck that burns gas, a Ford truck that burns diesel, a Ford car that burns gas, a Ford car that burns diesel, don't even know if they make such a thing, a Ford van that burns gas, or a Ford van that burns diesel. Or I could have a Nissan truck that burns gas, a Nissan truck that burns diesel. The Nissan could be a car that burns gas, or the Nissan could be a car that burns diesel, or it could be a Nissan van with gas or a Nissan van with diesel. So that's my sample space, but as our sample space gets larger and larger, sometimes it's hard just to make a list of all of the possible outcomes. So in that case, we use what is known as a tree diagram. So let's look at how do we make a tree diagram for this. So this tree has three particular levels. Our manufacturer could be a Ford, or it could be a Nissan. So those are our choices for the first level is Ford or Nissan. At our next level, our choices are truck, car, or van. So from the first level, we're going to have as many branches off of each element as we have possible items at the second level. So we can have a truck, a car, or a van attached to the Ford. We could also have a truck, a car, or a van attached to the Nissan. And then at our third level, our choices are either gas or diesel. So from each node, each endpoint at the second level, then we're going to have a branch for each of these. So we have two choices here. So at each end, we're going to have two branches. So the Ford truck could be gas or diesel. The Ford car could be gas or diesel. The Ford van could be gas or diesel. The Nissan truck could be gas or diesel, gas or diesel, gas or diesel. And notice if we follow each path, that'll list our different possible outcomes for our experiment. It could be a Ford truck with gas, a Ford truck that's diesel, a Ford car that's gas, a Ford car that's diesel, a Ford van that has gas, a Ford van that has diesel. Now, these are things I just made up. Some of these combinations may not actually be manufactured, but hopefully you get the idea. Nissan truck that burns gas, Nissan truck that burns diesel, Nissan car that burns gas, Nissan car that burns diesel, Nissan van that burns gas, and a Nissan van that burns diesel. So those make up our sample space. Those are the different things that could happen. Now, the topic that the counting principle says if one event occurs in m ways and another event occurs in n ways, the number of ways that events can occur in sequence is their product. And it says that can be extended to however many events. So if we had 3 different events, in the first event, there are m ways it could happen. The second event, there are n ways that could happen. In the last event, there are t ways it could happen. To get the different number of combinations, we multiply those together. So if we extend that to this particular situation, at our first level, our first event is that it's a Ford or a Nissan. So there are 2 things going on there. Our second event is that it's either a truck, a car, or a van. So there are 3 choices there. And our third level, the choices are gas or diesel. So there are 2 choices there. So let's just look at just the first 2 layers. So the first 2 layers, notice Ford truck, Ford car, Ford van, same thing with the Nissan. There are 1, 2, 3, 4, 5, 6 things that could happen out of these combinations. The first one could be attached to 3 different things. The second one could be attached to 3 different things. So out of 2 things that could happen in the first event, they could be connected, each of those could be connected to 3 items in the second event. So this 2 gets multiplied times 3. Notice that's 6, which is 1, 2, 3, 4, 5, 6. So up to this level here, there are 6 things that could happen. But our experiment is not done. We have another event, and that is gas or diesel. Each of the 6 layers that we already have, each of those could have 2 different things that could happen. So out of the 6 things that we already know that could happen, each of those could either be gas or diesel. So if we multiply this 6 times the 2 that could be attached to each one, that gets us 12 possible outcomes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's our counting principle. Multiply the number of outcomes for each event together, and that'll tell us the total number of outcomes that we could have. So this is a similar example. The manufacturers could be Ford, GM, or Honda. The car could be either compact or mid-size, and then we have 4 color options. So the question might be, how many different ways can we select a manufacturer, a car, and a color? And it says use a tree diagram to check our answer. For this one, we won't check it with a tree diagram. But at our first level, we have 3 manufacturers. At the second level, we have 2 car sizes. And at the color level, we have 4 different colors. So if we multiply those together, 3 times 2, that's 6 times 4. There are 24 choices that we could come up with. For each color, there are 2 different sizes. So that would be 8 choices. And then for each of those 8 choices, there are 3 different manufacturers. Those 8 choices could go with a Ford, those 8 choices could go with a GM, or those 8 choices could go with a Honda. So 8 3 times gives us 24 different things that could happen. So that's what's known as our counting principle. Oops, skipped a little bit too far. Let's work through this example. The access code for a car security system consists of 4 digits. Each digit can be any number from 0 through 9. So we have 4 digits. And we could pick numbers from 0 through 9, which if we look at numbers 0 through 9, that's actually 10 numbers. 0, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 10 possibilities for each number. So how many access codes are there possible when each digit can be used only once and not repeated? So let's suppose each digit can only be used once. So when we pick our first number, it could be any of those 10. But once we pick the first number, if we can't reuse that same number, that only leaves us 9 numbers for the second choice. So we've used one number, another number, so that leaves us 8 for the next one and 7 for the next one. So if we want to know how many ways are there to pick an access code, if we can't use the same number twice, we just multiply those together. So 10 times 9 times 8 times 7, 5,040 different ways of picking the access code. So if that's the way your code is set up on your vehicle and you forget the code, if you're just randomly guessing, you only have a 1 out of 5,040 chance of guessing it correctly. You could potentially have to go through over 5,000 combinations to find the right one. Now part B says, well, how many access codes are there possible if each number can be repeated? So if you can reuse a number, that means we could use 1 of 10 numbers for the first one, 10 choices for the second one, 10 choices, and 10 choices. So we have 10 times 10 times 10 times 10, or we could call that 10 to the 4th power. If we multiply that out, that's 10,000. So if we can reuse numbers, then there are 10,000 different combinations that you could come up with for a 4-digit number there. Now choice C, or the third option, each digit can be repeated, but the first digit can be only a 0 or a 1. So we can repeat numbers, but the first number has to be either a 0 or a 1. So that means we have 2 choices for that first number. Then the second number, it can be any of the 10 numbers. The third one can be any of the 10, and the last one can be any of the 10, because we said those are repeatable. So if we multiply those numbers together, there are 2,000 different combinations, if those are the ways that we're allowed to pick numbers for each slot. So this counting principle helps us determine essentially the size of the sample space. How many different outcomes are there? How many different things could happen in our particular experiment? So another topic we want to discuss are the types of probability. So let's go back up one. The first type of probability we'll discuss is what's called classical probability, also known as theoretical probability. It's, in theory, how likely is it that something occurs, that a particular event occurs. We take the size of the sample space, we put that on bottom, and then how many ways there are for our event to occur, we put that on top. So, for example, looking at this example, if we want to know what is the probability of picking a Ford that burns gas, in this experiment there are 12 different things that could happen. So 12 is the size of our sample space. Now let's look at, out of those, how many of those are Ford vehicles that burn gas? So here's one, And here's one. So there are 3 Ford vehicles that burn gas to choose from. So if we were randomly selecting, we have a 3 out of 12 or a 1 out of 4, or we could call that a 0.25 chance of selecting a Ford that burns gas. So that's in theory. If I just am randomly picking the vehicle, eeny, meeny, miny, mo, or I'm just drawing the names out of a hat, that is the likelihood of choosing that particular vehicle. Let's do another example. Let's do this one. Let's find the probability of getting 2 heads, which that's event A if we use this description. So our sample space has 4 elements in it. Out of those 4 elements, there's only one way to get 2 heads. So this is the number of outcomes that match our description, and this is the total sample space. So if we flip a coin, flip 2 coins, there's a 25% chance that we get 2 heads. So notice we didn't conduct any, we did not actually flip any coins. We did not actually pick a vehicle. We're just saying, out of the possible things that could happen, how likely is it that we choose this or that we choose that if we're only choosing at random? So that's theoretical probability, classical probability. The other type of probability is empirical probability or statistical probability. It's based on observation that comes from actually running an experiment. So if I just looked at my sample space for flipping 2 coins, then I would see that there's a 25% chance of getting 2 heads. But no experiment was conducted. So if I were to run an experiment and I toss 2 coins, and then I toss 2 more coins, and then I toss 2 more coins, and I list the outcomes, let's just do that. You could sometimes people use computers to simulate an experiment like this. Sometimes they actually take the coins and do the experiment. So let's say on the first trial, we flip a coin and we get heads and tails. And we flip the coin the next time and we get tails and tails. We flip the coin and we get tails and tails. And let's run through 10 iterations. So the next time we get heads and tails, then tails and heads, heads and heads, tails and tails, tails and heads, heads and tails, and then heads and heads. So theoretically, we determined that there was a 1 out of 4 chance. There are 4 different things that could happen. One of those is heads and heads, theoretically. But if we have conducted an experiment and we have collected this data, and from this data, we want to determine the probability of getting 2 heads, then from observation, out of 10 trials, 2 of those were heads and heads. So 2 out of 10, which reduces to 1/5, or 20%. Notice that's different than the theoretical probability. The theoretical probability was 1 in 4, or 25%. But if you conduct the experiment, you might not get exactly that. In this case, we got 20%. Now, the law of large numbers is just a law that says as an experiment is done over and over and over. So if you let your number of trials get more and more and more, so instead of tossing 2 coins 10 times, let's say we toss 10 coins 200 times or 10,000 times. As our number of trials get larger and larger and larger, the theoretical and the empirical probabilities will get closer and closer together. We know that unless the coins are fixed, unless they're unbalanced, then we would expect a fourth of the time to get two heads. But if we only flip the two coins one time, we might get two heads, we might not. But as we flip the two coins more and more and more times, our empirical probability, our probability from observation, is going to get closer and closer to the theoretical probability. So theoretical, we're not running any experiment. We're just thinking about what would happen in theory. Empirical, what have we observed from conducting an experiment? And I don't think I gave you that formula. But for the empirical probability, it's basically the number of trials. They call it the total frequency. But we could say the number of trials. And on top, that's the frequency or the count of that event. So whatever we're looking for, this is how many times did that happen. So for ours, we did the experiment 10 times. We were looking for two heads that occurred twice. So that's how we conduct the empirical probability calculation. So let's talk about types of probability more. We talked about theoretical probability and empirical probability. Let's talk about subjective probability. Subjective, that's contrasted with objective. Objective is something that is concrete or that has good evidence to back it up. Subjective is often things that are based on feelings. For example, a doctor may feel that a patient has a 90% chance of full recovery. There are no calculations that the doctor sat down and said, okay, this patient has A, B, C, and D wrong with them. There's this chance of getting over A, there's this chance of getting over B, so combined, the patient has a 90% chance of getting better. That's just an estimation based on feeling. Could be an educated guess. It's just something they have a feeling about. Often when we hear statistics, sometimes in normal everyday conversation, unfortunately, a lot of those are subjective probabilities. If someone's not a meteorologist and they haven't watched the weather, they just look at the sky and they're like, well, looks like there's an 80% chance of rain today. If they've not collected data or not watched the news or read anything, that might be just based on an educated guess. That might just be from experience of knowing which way the wind's blowing, what has been happening lately, what the humidity level is, what the type of clouds there are, and just making a guess. Where hopefully when you read an article, the statistics, the probabilities that are given are more than just subjective. They've come from data that's been collected and percentages that have been calculated from actual data. So they give us a few examples and they ask us to classify these. If you say that the probability that you'll get an A on your next test is 0.9 or 90%, well, how did you make that determination? How did you determine that you're going to make an A on the next test? I mean, you might do things like studying, listen in class, like that increase your chances of making an A, but how did you come up with 90%? That's just probably just an educated guess. So that is a subjective probability. If we say that a probability that a voter chosen at random will be younger than 35 years old, without knowing more details, it's hard to know exactly which type this is, but it could be that a survey was given, or that a census was given or collected, and we determine how many voters there were in the survey or in the census, and then we counted out of those how many of them are younger than 35 years old. We did a calculation based on an experiment, a survey, a type of experiment, and from that experiment we came up with a likelihood. If it comes from an experiment, then that's an empirical probability. Now, let's look at this one. The probability of winning a 1,000 ticket raffle with one ticket is 1 out of 1,000. If there are a total of 1,000 tickets, and out of those 1,000 you only have one of them, then that is a theoretical probability, or also known as classical. That comes from knowing the possible outcomes, knowing how many ways you could win, and calculating a probability. No experiment's been run, just made a calculation on what you expect to occur. Let's just make a few comments. When we calculate probabilities, probabilities cannot be negative. If you say I have a negative 20% chance of doing something, that's not possible. If you have a 0% chance of doing something, that means you're guaranteed that it's not going to happen. And there's nothing lower than not being possible. If something is not possible, that's 0. That's as low as it gets. The highest a probability can get is 100%. If there's a 100% chance of success, something can't be more likely than guaranteed. So as a decimal, 0% is 0. 100% is 1. So that's why they say that probabilities always have to be some number between 0 and 1. They could include 0, they could include 1, but it can't be more than 1 or less than 0. The complement of an event is just the likelihood of that event not occurring. It's just everything else. If we go back to flipping the two coins, if we list all of the possible outcomes, and I say, what's the probability of getting 2 heads? We said that was 1 out of 4. If we say the probability of not getting 2 heads, that's everything else. So there are 1, 2, 3 ways of not getting 2 heads. So those are complements. If we call one event event A, the complement of that event, we put a bar over the A to denote the complement. If, notice, an event and its complement don't have overlaps. Either an event happens or it doesn't happen. So when we add the likelihood of an event happening and it not happening, that will always total 1. Often we use the fact, if we want to calculate how likely is it for an event to not happen, we take 100% or 1, we subtract how likely is it for an event to happen, and whatever's left is the likelihood it doesn't happen. For example, if I know the probability that an event occurring is 70% or 0.7, then the probability that that event does not occur is whatever is left over. So 100% minus 70% is 30%. 1 minus 0.7 or 100% minus 70%. That's what's left. So those are complements. All right, and that's pretty much section 1 for chapter 3.